and then horizontal, and these are important parameters inside the dispersion model. You've got to know where you start from to get downwind to figure out how that dispersion is happening. If you don't know where you're starting from, then you can't expect the concentrations very close to the source to be correct. So from this then we were able to pull this data out, and this data then was used in the most recent models from the Federal Aviation Administration, now called AEDT, and it starts the plume at the right size and allows for the thermal buoyancy. However, we found out that we should have gone farther. And so we started looking at time series, and the time series showed us that as it leaves the runway, not only is the plume getting bigger, but it has these characteristics of rise and that weren't really included in the model. Right now, it's being modeled right at the runway. It shouldn't be modeled there. It should be modeled when it fits the plume, which is actually an offset to the runway. And that's why right now the FAA is getting problems on their concentrations at the fence line of the airports. So we need to figure out how to change that. So we're going back now. We're looking at the LiDAR data again to figure out how these parameters are changing. And then from that, we'll be able to go back and have a better fit to that model. So this is kind of a simplistic idea of a Gaussian model. And of course the Gaussian model, anybody know where we got the Gaussian model from? We used for dispersion modeling? Well, I would like to say this is a great brand new idea, but actually it came about in the 30s. And we had to figure out the radionuclides from above ground nuclear testing where they were going, so we invented this model. Someone says, hey, this might work for air pollution as well. So we adapted to air pollution and we've been using it ever since. So one of you out there, I hope, will maybe get us past this stage and go to the next stage of real dispersion modeling. Well, but when we took those LiDAR results, what we could do then is knowing the standard deviation in the Y and the Z and Y across the plume, we could then fit where that plume really started and where it fit into the dispersion process the best. This now is giving us better results, and we're in the process right now. FAA actually is just about to fund another stage, and we're going to make changes to that model to make it more accurate. But we have some other differences too that we need to look at. Right now, inside AERMOD, it uses what's called an area source. An area source allows all emissions to come uniformly out of a defined area. That defined area is the width of the runway. Well, we don't have emissions coming off the edge of the runway. We don't have emissions all over. We have them in defined points. So that area source then has some problems. It's an easy way to model, but since the emission rate's in grams per second per square meter, it has this uniform emission, but we know that's not happening from an aircraft. Also, we can't change the sigma y, or the standard deviation in the y, which is a key parameter for the model, because it's fixed by the runway. And that's not right either. The other problem is it's just two-dimensional. We need more than that. We need to be more robust. So we're looking now at a volume source, which now has units in grams per second, which would allow us to allocate those emissions where they're really at. It also allows you to set both the lateral and vertical plume size, standard deviations, will fit that plume better inside that overall model. And then if we account for that plume size inside AERMOD, we ought to have more accurate results. It's also three-dimensional, so the air can blow through it. It can't just come out the top and go downwind. It blows through the source and allows that real dispersion to take place. And this is very important around airports because although airports don't emit as much as our motor vehicles over a year, they are very large sources. And so people, as they move closer and closer to the fence lines, are being affected more and more. And so things like particulate matter and NOx are very important considerations for aircraft. So when this plume lifts off, we also have a problem. If you define an area source, so you've got this flat surface here and saying emissions are coming out of that, that's not right either. So that volume source makes a much better way to do this dispersion. So we're going now from an area source, or a flat area that emissions come out of, to a volume defined in 3 dimensions where the emissions are coming from, and we can define that volume where the aircraft is really light. There are some problems. Some aircraft have the wings or have the engines under the wing. Some have them on the fuselage. Some have 4, some have 2, some have wider distributions. So we'll have to do it by types, but we still think we can get a much better idea. Then when we come back into AERMOD, we'll be able to really use AERMOD without changing it. The release height, the symbolized sigma z, can be much better specified. We will have a much more accurate model, we think. For those of you who don't know, if you try to change a dispersion model, they have what's called Appendix W. And this is a process to prove that model works. It takes at least 5 years. FAA can't wait 5 years to do their NEPA analysis. So this would be the first step, and then in the future, we can start to develop other models that will take longer time. So then, if we're going to take longer time, we're going to different models. One of the models that really makes sense is a puff model over the Gaussian plume model. Remember that diagram we had of the Gaussian plume model? It's steady state, a constant model. It assumes the emissions are always coming out over time in a constant way, and that the weather is behaving in a constant way. All of you know weather doesn't last. I mean, if we stay the same 10 minutes, we're lucky. So that's a problem in itself. And we also know that as you get real down, as you get farther from the aircraft, that's not a continuous source. That aircraft comes past you, the plume comes and goes. That has to be accounted for. So there's got to be a better way for aircraft. So we took taxi data from radar and we put it into simulation models. A lot of your faculty are working on simulation models here. If you can get involved in those projects, I really recommend it because I truly believe we're going to go to simulation in the future. In the past, computer resources always held us back. I think we're now past that point. And I think simulation of motor vehicles and aircraft, how they really move and what the emissions really are going to give us far better numbers in the future. We got the required airport activity from the airport, and we started puff model development, and we started looking at it. Now this was the first phase, so we only did it while the plane was on the ground and islands. The difference between a puff model and that Gaussian model you saw is instead of just this continuous plume that we saw before, we take account of each time puff or release. Inside those puffs then, we can have them move with different wind patterns. We can have chemistry taking place. We can allow for the expansion that might occur in a slightly different way. We can allow for the aircraft moving or the motor vehicle moving. So we think a puff model is a much better way to go. The model we derived, I'm not going to go through all of this, but had the same input and output that you might expect of any model. But I did want to cover 3 key things that happen inside the model. One of the things that we had is if you have all these puffs every second, and you're trying to simulate, say, 86,400 seconds in a day or something, that gets a little complicated. So we had to have ways to make it a little better. So we did move each puff, and we did disperse each puff. But at a certain distance, these puffs start to blend together and become a single puff. So we allowed, due to the weather conditions, for these puffs when they got close together to merge, and that reduced the amount of puffs we had to track inside the computer. And so instead of multiple days on a computer run, we could do it in a couple of hours, which no airport operator is going to wait multiple days for results, so we had to do something. So we think this is really good because we still keep track of each puff in its critical times, especially in those chemistry times, but then we merge them, we reduce the complexity of the model, and make life easier. After you determined aircraft movements, a couple things we found out too. ICAO is the governing body for the world for aircraft emissions. Aircraft are worldwide, right? So you don't just have a national standard, you have a worldwide standard that everybody follows. And that's set by ICAO. And ICAO then comes out with these emission standards. Right now they have 4 modes for aircraft: taxi, takeoff, landing, and climb out. We found out that if you looked at the emissions that we measured with probe testing in the back of aircraft that the idles were close. So we had to adopt that a little bit to get some better results. We also, when we developed the model, we developed it on atmospheric stability classes. You know, I don't know if you've seen those before, A, B, C, D, E, F. Those are kind of now being phased out for atmospheric scaling, where you can keep track of what the atmosphere is really doing in a much more complex way. We probably should have gone to atmospheric scaling, but stability classes were easier at the time. And with the resources we had, we went with that. Then we looked at the puff according to the mean wind. We looked at the thermal buoyancy. We looked at each aircraft type and the release heights and where it was released. And then we looked at second by second concentrations at the receptor. And that allows them in this puff model to follow what was happening on real time, not just over an hour like you get with AERMOD. So we looked at some assessments, and I'm going to show you the simple ones so we can understand what's going on. Imagine an aircraft taxiing down the runway, and then it gets, down the taxiway, and then it gets to the runway. One case is that there is no delay and it just pulls out on the runway. And another one, which is more often the case, is as it gets close to the runway, it has different points where it has to queue up. In other words, it can't just pull on the runway automatically. It has to wait for these other aircraft. So we wanted to see what would happen, and so we picked two receptor locations, one where it was just moving past, and another one where delays were happening to do an analysis. Well, we found out, of course, as you would expect, that without delays at R2, which it just passes by, the emissions stayed the same. You would expect that. But when we get to delays, of course, we start getting increased emissions over the hour. And that's what would be expected. So no shocking news there. The aircraft is there longer, it's emitting longer, and you're going to have a higher hourly concentration. But it's more than that. We've got to look at it in a time series of what's going on. At R2, when it came past, if we looked at it in real time, as the aircraft came by, there's a big increase as that exhaust of the aircraft comes by you, and then it falls off with time after that aircraft passes. So no delay, that's not a problem. But when you start to get delays, you start to get other things taking place. Here we are now, no delay, as you saw before, but now this is what's happening more in the real world. The aircraft gets there, you see this big slug, and then it kind of settles down while the aircraft are all sitting there in a row, and then it starts to fall off. So let's think about this a second. If you have a continuous Gaussian model over the hour, you're going to try to make your emission factors right, but it's still over the whole hour the same concentration. But that's not what's happening in the real world. In the real world, we got a spike where it's really high, but then it falls off very quickly. And so when you look at the time average, which is the way all the National Air Quality Standards are written, it makes a big difference. Continual versus this peak and what happens in a short period of time. So we have to look at that. So we picked these different places around the airport where we might be able to do some good modeling on this taxi idle and what was happening. And we found some interesting results. So we went back to EDMS, which is really AERMOD, which is now an AEDT, very confusing, I know. But it's still AERMOD. It's still that EPA dispersion model. And we found out that in every case, whether we used 2 years of radar data or where we did a simulation of those aircraft movements, EDMS was always giving us a much greater concentration than what was really happening. Any idea why that is? Why would AERMOD give us that high concentration compared to the simulation model? What's the difference between those two models?
Average.
Exactly. That continuous concentration is too high. And over time, since it's staying there, it's staying too high. That's not really what's happening in the real world. If we account for these plumes as they really go by in real time, we find out that they're not there that long. They move past, and while you might have a spike, and the peak concentration might go higher than we predict with AERMOD, the overall average is lower. And so right now we're doing all these airport analysis using this model, and we're over predicting what's really happening. The saving grace, of course, is that we have distance a lot of times between the runway, the taxiways, and where the people live. But that's becoming less and less happening. If you've ever gone up to Providence, Rhode Island, they have houses now that have moved right up within about 300 feet of the runway. And so now we're getting to a point, this happens a lot in Europe as well, where people are getting close, and this is becoming important. And if we allow these over-predictions to occur, not only are we not seeing the peak, and what really might happen in the peak, but we're not seeing what they're exposed to over time, and we can't really do a good job on the health impacts that are occurring. And after all we're trying to do with air pollution, the final goal is to reduce the impact on people's health. Right? Nothing else really matters. So if we're not doing a good handle on those health impacts, are we doing our job? So if you look at them, if you just use a standard model, which is constant, you see these hot zones all the time that really don't occur. They're just there because that's where the emissions are all the time. Whereas if you use a plume model, then we see what that plume happens, and then I have simulations that I didn't put them in here because I found out PowerPoint doesn't always work the same every way, and I didn't want to freeze up the PowerPoint. I do have them if we have time later. But what happens then is that you take all of these plumes, you can allow for when the wind changes and stuff, and then you sum them up over the hour and average them, and then you find out what's really happening in all these different places and what the average concentration is going to be. This tells you where you really might have a problem compared to where you're predicting a problem that doesn't really exist. So this is the future, simulation modeling. And again, a lot of your faculty are working on it. I really recommend that if you're not involved, at least you pay attention to what's happening, because I think you'll see those a lot in the future. So for the pump model applications, we have these time-varying concentrations. These sub-hour concentrations can be accounted for. The overall hourly concentration is better accounted for, which allows us to look at the National Air Quality Standards and health effects in a much more robust way. We have the ability to use the monitoring source data to look at the second-by-second aircraft movements now in major airports. They keep very good records of what's happening in the airports for those aircraft. It allows for a more accurate health effects estimation, we said, potential for better inclusion of atmospheric chemistry, which is something we really can talk about, but remember, a lot of these pollutants change. When it comes out the back of the exhaust of an aircraft or a car, it's mostly nitric oxide, NO. It quickly interacts with the atmosphere and becomes NO2, which is really what we control. Well, we don't really have a good handle with these constant models on that rate. We have some things that we tried to do, a plume model we've tried, an ozone limiting model, but they really don't tell us what that real concentration is of NO2. With a puff model, we would be able to put in something like first order rate reaction chemistry, and we could keep track then of what's happening in each puff, and as it changes, then when we sum it up, we get that true value of NO2 as compared to the total, which is called NOx or NOx. We have better visualization of air quality impacts. We can show people where those plumes are going. We can show what might happen at their particular house. Anybody that's ever been to a public hearing, one of the questions you get is, what's happening in my house? Well, they can show them. And that goes a long way to helping them understand what's going to happen for a project. It gives better uncertainty assessments and a better cause and effect assessments. So I think this is what's going to happen in the future. As I said before, this can't happen overnight, a minimum of 5 years, but it has to start somewhere. So we think the puff model is better for the taxi movements, and we think it will be better for all movements in the future. We think it has the benefits of time-varying visualizations far above what you can show with a constant model. And it has the ability to show what the real concentrations are, not those average concentrations of the emissions happening over the whole hour from the same locations, even though the aircraft is not there. And we think that it gives us the effects of delays on aircraft better, so that When we start to design these airports and delays and high-speed taxiways and ways to get those aircraft better into the air, it gives us a better way to make those improvements. Right now, one of the big things facing airports is not capacity, it's environmental capacity. So this is a big constraint on airports beyond what they could actually handle as far as operations. We need future work. We've got to improve the fidelity of taxi emissions. We need weight dispersion and drag effects, which we didn't have in this model. We need more accurate position data. In other words, we've got to work with the airports more often. We need better handle on the exhaust engine temperatures. The aircraft manufacturers have this data. It's proprietary right now. We were able to get some, but we're going to need to put that in a way that we don't give away any trade secrets, but at the same time can put it into the model. We need better computational hardware. Any of you that come up with better ideas to make the computer faster, we really need more speed. And we probably want to go to atmospheric scaling instead of these little glasses. So, besides the question of why am I standing in front of the jet intake, I'll be glad to answer any questions that you might have.
Yeah, we have a few minutes here to answer any questions. Roger, I'll start out with when you talked about these fuel, a lot of these EPA moves models was derived from the old auto oil complex model. 25 years old now, right? Do you think this is a problem with auto oil natives, or is this a problem with the way it moves?
I think both is the right answer. Because first of all, we need more